Okay, so that now leads us on to the sort of the biggie. So this is about correlation between two quantitative variables. And if you do an introductory statistics course, you tend to spend a lot of time on this. So we're not going to really be doing statistics with this, but I want to explain the principles and show how we do particularly how we do the exploratory examination of this kind of data to decide whether it's worth doing some fancy statistics. So we're starting off, this is this Washington bike rental data again, and we've got three variables here. So we've got daily temperature, so this is the average temperature on each day. So it's a 2-year period. There's about, I forget exactly, but about 730 days of data. So that's the average temperature, that's the humidity, average daytime humidity, and that's the number of bike rentals. And I've just put the 5 numbers there so you can have a look and get an idea of what the numbers are looking like. So the median rentals was 4,500. The lowest rental day was this one. That's when Hurricane Sandy hit Washington in 2012, in October 2012, and they shut the whole city down, switched off all the public transport and so on. Okay, let's have a look at a time series. So there's the time series, and I've smoothed it, and in this case I've smoothed it with a 31-day running median. Now, 31-day running median is done the same way as you do a 3-day running median, except the end rules are a bit more complicated, but it's the same general principle. So you can see there is some, so these are numbers of days. So somewhere around there you've got 365, so that's a year, and then we've got the second year. My understanding is that 2011, that's the first year there, was the first year they ran this bike rental scheme. And so what we're actually seeing when we look at this data is growth from year 1 to year 2. So the second hump, if you like, there is showing that the scheme grew. So what I'm going to do in the rest of this analysis is just use data from 2012. And then the reason I'm doing that is just so things don't get a little bit mixed up, because I've got 2 years where one was busier than the other. All right. Now, this is a box plot of bike rentals over the 2 years, and you would really be lucky to find a more symmetrical, perfect looking box plot than that. There's no outliers, and it really is very symmetrical. I've also got a box plot here. This is just for November and December 2012, so the last 2 months of 2012, and so you can see there are outliers there, and it's not as symmetrical. So this is something you need to be aware of when you're looking at data that comes from a time series. You can have situations where there are no outliers overall, but there may be local outliers. All right, so the classic plot that we use when we have two quantitative variables is we use something called a scatter plot, and that's what a scatter plot looks like. So the way you read that is on the x-axis here you've got the humidity, so this is in percent, and the y-axis we've got the number of bike rentals. And you can see, you know, if you look at an extreme case at 80% humidity, you've got a day there where, you know, there was about, I don't know, 1,600 or something bike rentals, and if you go up further, you've sort of got a couple of days in that general region where you've got close to 8,000. So there's quite a wide range of you know, bike rentals for a particular humidity, average humidity reading. If you really squint at that, you might see, I'm not sure what you see. Some people would probably say, oh, it seems to be, maybe it's trending down like that. Other people would look at it and probably say, maybe it's a bit curved like that. Sorry, let me just check the chat here. I've got a few questions to catch up on. Why did I pick, whoops, where are we? Okay, why did I pick November and December? I picked November and December purely to illustrate the idea that there were local outliers. That's all. There's no particular reason apart from that.
So each of the green dots is a day, right? In those 2 months, in those months.
Yes, there could be days that are overlaid on top of each other. So I'm not sure if there's exactly 730 dots there, but that's right. Each is a day. Yeah. So it's yeah. So we always look at these. Whenever you've got quantitative variables, one of the first things you do is you look at all these scatter plots. You do a scatter plot for every pair of quantitative variables to see if there might be something that's worth investigating. Now with this one, eyeballing that, I find it pretty hard to tell, but I'll show you in a moment what the actual story is. So what I've done is I've added here a line. Now, let me tell you about the line. So this line represents something we call a linear model, and what it does is it starts with the assumption that the relationship in the real world between humidity and rentals is a kind of straight line relationship. That there's just a simple kind of proportional sort of relationship, and the way the location and the slope of that line is calculated is basically about minimizing prediction error. Okay, so I'll try and make this clear. So if I just look at that line, what that says to me is this model thinks that there is a pretty slight decrease in rentals for every % increase in humidity. I have the actual number down here. So the slope on this is -12. So what that means is, what this line says, if we accept this line as a model of what's happening with humidity and bike rentals, is it's saying the model estimates that for every increase of 1% humidity, the number of bikes rented goes down by 12. But the question we've got to ask ourselves, one question is, the big question is, how good is this as a predictor? We should also ask ourselves, is it plausible that it's a straight line relationship? But we'll get to that in a moment. So another way of putting it is, if I know what the humidity is, how much information does that give me that I can use to estimate how many bike rentals are going to be made on that day? And Sarah, it is a line of best fit, or commonly known as a regression line. But I don't want to get too much into the detail of that just yet. So this is it's a prediction model essentially. So let's just look at the line. So what I've done here, I've picked one humidity value. So there was a day when the humidity was 52.4583%. That's a remarkably accurate humidity reading. So I'll explain this, Sarah, how you can do it to work it out. So let's have a look at. I've chosen this particular day. So this was a day in November 2012, and it was a working day. It was a Friday. The weather was good. The average temperature was 8.2 degrees Celsius, and the wind speed was 11.5, which is not. It's pretty calm. And there were 5,698 bike rentals that day. So if we draw a line, so this line here, that is 52.98453. Okay. All right. So we draw the line up. We draw this a little dashed blue line up there till we get to our model. And then we go across to the bike rentals. And there we have the model's prediction of what the bike rentals will be. So the model predicts 5,704 bike rentals. Okay, so that number there is 5,704. Okay, so that's the prediction. The actual number of bike rentals on that day was 5,698. Okay, so the difference is only 6 bike rentals. Okay, so for that particular day, this was an extremely accurate prediction. You know, if that happened to be the day when you decided to test the model, you would have been most impressed because you got a very accurate prediction. But I have to tell you, I chose that day because that was the day where the model worked best. If we now add back in all the other points, so what we can see here is I've now got 2 blue lines, and those 2 blue lines there, they cover humidity from 50 to 55%. Okay, and we've got a number of days that had humidity in that range. There's a bunch of them up there, and it includes, as you can see there, it includes our Friday in November 2012, where the model was pretty much spot on. But you can also see that there's a bunch of days where the model is hopelessly out. So instead of 5,704 days, for this day here, whenever it was, you only actually got 2,000, or less than 2,000, 1,900 and something bike rentals. And similarly, you've got some days up here, you've got one up here which is pretty close to 8,000. So what you see from looking at this is this single line model here, this straight line model, this linear model, is actually a pretty poor predictor. Okay, so I might get you, Sarah, would you mind just elaborating on your last question there, Sarah?
How do you get, like, how did you decide, like, where to actually, like, 50 to 55, like, of humidity to the rentals? Like, what makes you decided to choose those data plots? Was it because it was the most, what seemed to be the most central point of the data?
No, it was simply, I just wanted to, what I did, the way I did this was I thought, okay, I'll find the day on which the model worked best. Mm-hmm. And then I thought, to illustrate the how good or bad the model is, I'll just choose a little humidity range around that, because there was only one day that there was only one day that had 50, whatever it was, 50, what was it, 50 something point, where are we? 52.4583. There was only one day that had that humidity value. So I thought I'll look at a little range, and then we can see a bunch of other points that are fairly close to it. but where it's really very inaccurate, very, very poor prediction. That's all. So my starting point was just for illustration. I'll show you a day where the model worked really well at a particular humidity level, and then I'll show you some other days with a fairly similar humidity level where it didn't work very well at all. Okay. So this now is a box plot that shows you the bike rentals for all the days between 50 and 55%, and I've put little vertical lines on the box plot to show the actual data points. But you can see when the humidity is between 50 and 55%, in that 1 year time period, you've had bike rentals of between about 1,900 and well over 8,000, probably close to 9,000 there. Okay, so this single line model is not doing a very good job of prediction. Okay, all of these points inside those two vertical blue lines, they should all be concentrated around the line. They should all be concentrated in that little range just there. So
would you say there's a lot of sort of, it's not really close to the real what's happening? It doesn't represent what's happening in reality.
That's exactly right. It's a very poor predictive model. I mean, I go on to actually give you some numbers on that, but the thing is, that model, so this is a thing, as we'll see, this is the kind of simplest example of a modeling technique that is used in a huge amount of research. This comes up again and again and again when you're looking at academic papers, and it's used a lot in industry. This is a statistically significant model. Okay, so it's quite possible that you would find a model like this in an academic paper, and the author would say the results were statistically significant, and they would quote a small p-value. But what actually is the case is, although it's statistically significant, it's a very weak correlation, and that's what I wanted to talk about next. So this is where this Pearson correlation coefficient comes in. So that's a number which tells us how good the correlation, how strong the correlation is, or the association between humidity and rentals. And the correlation coefficients, or Pearson ones anyway, they're always between -1 and 1. So between 0, but greater than 0 means there's a positive relationship, and less than 0 means there's a negative relationship. So in our case here, we've got a small negative relationship. If you have a Pearson correlation coefficient of 0, that means there's no association. So in this case, what we actually have is a very small correlation coefficient. So it's negative 0.081. So that's regarded as a very weak correlation. It's nearly 0. Okay, but it's statistically significant, and this is why that word significant in statistically significant is such a trap, because it suggests to you that there's something important happening here, when in fact there isn't. Now we also, when we do this, we also talk about the square of the correlation coefficient. So that's called R squared. And in this case, R squared is 0.0079. That's 0.79%. And that is interpreted as how much information the humidity gives us about what the rentals are going to be. So in other words, for that model, that line, it's only giving us a tiny, tiny bit of the information we would need to predict what the bike rentals would be. So to answer our question, how much does humidity tell us about what the bike rentals are going to be? What this is telling us is, assuming that the relationship between humidity and rentals is a straight line relationship, humidity tells us almost nothing. It tells us a tiny, tiny, tiny bit, but it's certainly not enough that we would use it to make any kind of decisions.
So is that because there's such variance and such?
Exactly, yeah. There's so much error. So the way these models, this line is found, is your computer goes through a procedure to find a line of a height above zero and a slope that minimizes the amount of error. So it's the best line that models the data, assuming there's a straight line relationship. But it can still be terrible. It can be the best one, but it can still be terrible. And this is the case where it's the best line, but it's a terrible predictor because there's.
So should the line be used or not?
Sorry?
So should the line be used or not?
I wouldn't use it. I mean, what use would it be? The errors would be so great. You think about it in a practical situation. You're trying to plan having enough bikes available on Friday, and you've got a weather forecast that tells you what the humidity is going to be. This tells you almost nothing, even though it's statistically significant. It gives you so little information about what the rentals are going to be that it's pretty much worthless. Now I'll just quickly show you the story with temperature, because temperature works much better. Okay, so this is the scatter plot for temperature. And you can see, looking at that, there's a much clearer relationship. This time it's a positive relationship. The model slopes upwards, and it's a much bigger slope. So for every degree of temperature increase, this straight line model says that the bike rentals will go up by 154. It's also statistically significant. And when we look at the correlation coefficient in this case is 0.71, and that's regarded as a strong correlation. And when we look at the R squared, that's 0.51 or 51%. So this is telling us that temperature, assuming it's a straight line relationship in the real world, temperature is giving us 51% of the information we need to estimate the rentals. So that's a much better predictor. But what we might query with this one is, when you look at it, it doesn't look much like a really straight line relationship. Okay, it sort of goes up and then it curves down, and that makes theoretical sense, because you can imagine when it gets to 30 degrees, or close to 30 degrees, it starts to get too hot for people to want to ride around on bikes, particularly if they're riding around the city while they're working. So we might do better at predicting if we used a different model, not a straight line model, but a model that could take into account the fact that in reality it's a curved relationship, not a straight line relationship. Does that make sense? Now we'll come back to these ideas. This is really I'm just introducing these in the context of exploratory data analysis, and we do other things. So one thing you might consider is, does somehow the humidity and temperature work together? So if any of you are familiar with how air conditioning works, how hot you feel depends on the combination of temperature and humidity. Okay, you can thanks, Eve. Yeah, you can. If the humidity is low and the temperature is high, you will feel cooler than if the humidity. What did I say? If the humidity is low and the temperature is high, you will feel cooler than if the temperature is high and the humidity is high. So when you design air conditioning systems, you design them to work within a particular range of combinations of temperature and humidity. Okay. Yeah, that's fine, Mickey. I'll stay around. So yeah, so that's
So could you, but like with this temperature and rentals, would it be okay for you to use that smooth? Was it how were you talking about earlier? How you smooth the average out, the median out, the smooth median?
so that's essentially, there's a couple of ways it's approached. So there are techniques that will sort of directly fit a smoothed line. And that's the sort of thing that happens when you start to use machine learning models and things like that. Another approach is you take your temperature data and you do the opposite of what I showed you Excel doing with that polynomial fit. So you use a polynomial fit thing to straighten the data. So you straighten the temperature data and you fit a line. And so then what you have to do your prediction is you take your predicted temperature, and then you've got to do a calculation with it, a quadratic equation or something, to get the and then you look that up on the straight line, and that will give the prediction for the rentals. Now, when I say you have to do a calculation and so on, that all gets done by software. But yes, your intuition there is absolutely correct. I'm pretty certain, I haven't tested it, but I'm pretty certain that you would get more information if you used a curved model, or a model that took into account the curvature there, than you would with a straight line model.